about deformation and strain. And this is chapter 4 in your textbook. Now, we talked a little bit about the difference between stress and strain and force previously. Deformation of a body occurs in response to forces, in response to strain. The forces acting on an area is strain, and that's what's going to cause the deformation. Now, most geological structures exhibit some type of deformation. Understanding how the forces and stress affect the components that cause deformation is crucial. So not everything is going to deform exactly the same, even under the same stress. Now this is going to require both qualitative and quantitative analysis. So we'll have to think about the process that's going on, as well as doing calculations about the process that's going on. Now, deformation is the collective displacement of points in a body. It can include three types of deformation. There's translation. It's not, I'm going to translate quartz into pyroxene like we translate English into French. Translation in this case is the movement from one place to another place. So it's like if you drive your car from your house to the school, you have translated your car. That's the meaning of this word here. So translation is the overall movement from one place to another. Rotation can happen without going anywhere. It's just spinning about an axis. So if you forget to disengage your emergency brake, you step on your gas pedal and your tire spins, but your car doesn't go anywhere. There was no translation, but there was definitely rotation. Distortion is a change in shape. That's what happens if you lose control of your car and hit a tree. Lots of distortion. Your car changes shape. Now, strain is the changes of points in a body relative to each other. So if part of it rotates and part of it doesn't, you now have strain. If part of it translates and part of it doesn't, you have strain. If the whole thing translates or rotates, you have strain, even though the individual body doesn't seem to have changed. Now, a displacement field is indicated by a bunch of vectors that are showing what's happening to each part of something. And we can subdivide it into three components: the distortion, the rotation, and the translation. So we can have total deformation shown at the top, where we had that square with a circle, and it ends up as a parallelogram with an elliptical type shape in it. Now, how did that happen? Well, we can break it into the three parts. There was some distortion, there was some rotation, and there was some translation. And they could have been happening simultaneously, or they could have happened one after the other after the other. When rotation and distortion components are equal to 0, we only have translation. This is like your car drives from your house to work and nothing goes wrong. You don't hit a tree, you don't spin your tires, you don't roll your car. It just gets from where it started to where it ends up with no rotation and no distortion. We call this rigid body translation. When you're driving a car, this is what you want. You don't want the other kinds of distortion. So rigid body translation, or simply just translation. Similarly, if distortion and translation equals 0, then we only have rotational effects. We call this rigid body rotation, or spin. This is a great thing if you're at a theme park and on a merry-go-round or a Ferris wheel. This is what you want. You don't want any distortion, and you don't want any translation. If that Ferris wheel comes off and starts translating, you got problems, kind of like you saw in the Pirates of the Caribbean movie or other movies like that where the big wheel comes off and starts translating and moving. If the translation and rotation components are 0 and it's only distortion, we simply call it strain. And strain is a component of deformation, not a synonym. It's only strain specifically if it's the distortion component of deformation. So deformation is all three or any of the three. Strain is specifically the physical distortion, which I may have misspoken on that on an earlier slide slightly. But what I'm saying right here on this slide is the accurate word choices. Now, deformation and strain are defined relative to a frame of reference. With translation especially, the frame of reference is everything. If you don't have a frame of reference, you don't know if it's moving. Even with rotation, if you don't have a frame of reference, it's hard to tell. The strain, the distortion, is a lot easier to tell if you're seeing the whole thing, but if your frame of reference is too small, you still might not be able to tell. Now, in deformation, we use an external reference frame. We're defining the translation and rotation according to an outside source, such as your car moving relative to the earth, or the rock moving relative to the outcrop, or the rock moving relative to the whole earth. So the frame of reference is very important. To us, the earth doesn't feel like it's moving, well, outside of like maybe an earthquake, but we know that it's flying through space very rapidly. So on an external frame of reference, the solar system, the galaxy, the universe, the Earth is moving. To a small frame of reference, like our office where we're sitting at our desk, the Earth appears stationary. Now, strain uses an internal reference frame. But again, it has to be a big enough reference frame that you're taking into account enough of the object that you're actually seeing the strain happen. It's basically looking at control points within the body and seeing that they are changing relative to each other. If you think about a shoelace, when you tie your shoes, the shoelace is changing shape compared to what it used to be. If your frame of reference is the whole shoelace, it's obvious that there's deformation happening. If your frame of reference was only a little segment of the shoelace that happened to be down between a couple of holes in the shoe, you might not detect any of the strain occurring when you tie your shoes because the frame of reference was too small. But looking at the shoelace as a whole, lots and lots of strain happen. It gets bent and folded and pulled and all kinds of stuff. Now, area or volume change is a fourth component of deformation called dilation. It's a kind of special case. Now, there are four components: the rigid body translation, or simply translation, rigid body rotation, or spin, volume change, or dilation, and strain. It's just strain, there's no other second word for it. Now, strain can be homogeneous, equal throughout. This means that originally straight lines are going to stay straight. Originally parallel lines are going to remain parallel. For example, if you look at something in 2 dimensions, like, because you have a cross section or a cross cut of your rocks, a circle ends up being an ellipse. In 3 dimensions, a sphere becomes an ellipsoid. I'll show some images coming up here. And if one or more of those 3 rules above do not apply, then it is not homogeneous strain, and instead it is heterogeneous. Heterogeneous strain is difficult to analyze. So what we try to do is break it up into a couple of homogeneous components. So maybe there was some homogeneous strain due to stress in one direction, then the stress field changed and there was homogeneous strain occurring in a different orientation due to the new stress field, and as a whole the strain that happened was heterogeneous. But if we break it into 2 separate events, we can see 2 homogeneous strain events, and those can be analyzed nicely and easily, relatively easily. So we have an initial condition. We have this little checkerboard pattern, and we have a circle in our 3-dimensional brick. Now, if we have the first case labeled B, we can see that there looks like some shear stress being applied. The thing is deformed. It has undergone strain. But if we look in the checkerboard, the straight lines are still straight. The parallel lines are still parallel. So that's good. The circular object now is elliptical. That's good. We look back at our list here. It hits all 3 rules. Homogeneous strain in image B. If we look at image C, on the other hand, we see, well, our lines are no longer straight. So we've already broken one of the rules. We can also, if we decided to look for parallel first, we would say, oh, look, they're not parallel anymore. It broke a rule. If we happen to look for the circle-ellipse relationship first, we would say, oh, that circular thing did not turn into an ellipse. It broke a rule. So in this case, it broke all 3 rules. So it only needed to break one to be heterogeneous strain. Now, looking at a real case, we can see something like this out on a mountainside. So how are we going to break this into homogeneous components? What are the different components? What things are we going to look at as a geologist? Well, we can obviously see that there's this curved thing here. curvature of a bed indicates that there's been distortion, there's been strain. And what we can look at is two limbs and a hinge. Now the hinge is down here, it's like the pointy part or the bottom of the curve. The limbs are the relatively straight sections. You think of it as, you fold a piece of paper, the hinge is where the crease is, and the limbs are the paper on either side of the crease. So the limbs are in the two squares, or rectangles rather, on the sides, and the hinge line is that line in the center. That's where approximately everything is folded around that. The hinge probably should be a little tilted to the right though.